Bridges are vital structures that allow people and vehicles to cross obstacles like rivers or roads. Their key function is to carry their own weight and additional loads while withstanding various forces. The simplest type is a beam bridge, ideal for short distances but will struggle with longer spans. Arch bridges use curved structure to support loads and compression, while cable-stayed and suspension bridges use cables to handle large spans. In our Spaghetti Bridge project, spaghetti behaves like real bridge material. It's weak in compression but strong in tension, which challenges us to design a structure that maximises tension and minimises compression failures. Our goal is to create the lightest bridge that can bear the most weight by understanding how internal forces affect it.
A truss bridge's design is notable for its strength and efficient load distribution, primarily due to its use of triangular units. Triangles are structurally superior to squares or rectangles as they resist deformation under pressure, making them ideal for weight-bearing structures. This principle applies even when using fragile materials like spaghetti. When glued together, the spaghetti gains strength through truss structure, allowing it to support significantly more weight than expected. The balance between compressive and tensile forces within the truss minimizes stress, which is vital when using materials that are naturally brittle. Additionally, truss bridges maximize strength while minimizing material use, distributing loads evenly to prevent any single point from bearing too much pressure. This material efficiency is crucial when working with delicate materials like spaghetti. Real-life examples such as Forth Bridge in Scotland and the Sault Ste. Marie International Bridge showcase how truss designs effectively manage both compression and tension forces, allowing for stable structures to withstand external forces like winds and vibration. In summary, the truss design offers both durability and material efficiency, making it ideal for constructing bridges with using materials as weak as spaghetti.
In creating our spaghetti truss bridge, we conducted thorough investigations, performed design calculations, and ran small-scale tests to ensure its performance. These steps were vital in refining the design and predicting its load-bearing capacity. We began by studying spaghetti's properties, noting its better performance under tensile stress than compression. Design calculations helped us to estimate load distribution across the bridge using the static equilibrium, aiming to prevent localized failures. We selected a Warren truss configuration for its efficiency and balancing forces, and used shorter beams to enhance the structural strength. While we did not use advanced software, we utilized CAD tools to model and visualize the brooding. This helped us to refine the layout, identify weak points, and experiment with different truss configurations to ensure stability and symmetry. We did miniature tests of the truss design, observing failure points at the joints. Adjustments were made by reinforcing glue application and ensuring beam uniformity. Testing different spaghetti thickness led us to use a 6-strand configuration for the key load-bearing elements. We predicted the bridge could hold 10 to 15 kg, whilst the actual bridge holds 6.5 before slipping. The structure remained intact, and no significant damage occurred. The issue was primarily due to the bridge's length rather than the structural failure.
Now that the bridge was complete, it was time to test it. The spaghetti bridge weighed in at a total of 108 grams. Our original estimate in regard to the weight of which the bridge could endure was somewhere between 10 to 15 kilos. When placing the spaghetti bridge on the platform for testing, it was clear that our group underestimated the length of the bridge, as it was barely sitting on the platform on either side. When placing the spaghetti bridge evenly on the platform, it was held on by a total of 5 millimeters per side. After remeasuring the total length of the spaghetti bridge, it came to a total of 360 millimeters. Although it was still testable, our prediction was that the bridge would more so rather slip off rather than break. This was simply due to the fact that it was not supported well enough on the platform, due to the bridge being in the shorter side. In relation to the placement of the weight applied to the bridge, it was placed in an area of which we believe was best supported, being in the center plus on the bottom level. This area also had the support of the Warren truss design, making it stable and strong. Once the spaghetti bridge was attached to the weight, it was time to apply force to the structure. As predicted prior to the testing, the bridge did in fact slip off the platform. It achieved and held a total weight of 6.5 kilos before slipping, which was very unfortunate.
By integrating research, calculations, testing, and modeling, we maximised the spaghetti bridge's performance, gaining valuable insights into load distribution in truss structures.